Okay, should we start?
All right.
Okay. So welcome everyone. Today I'm happy to share the tutorial of Michael on deep neural networks for assessing cortical responses to speech. So before it starts, I just want to remind you that you are free to ask questions anytime by raising your hand or typing it on the chat. If you have any technical issue with Colab, just type it in the chat and I will do my best to help you. So don't be shy, and Michael, the floor is yours.
Great, thanks a lot. So maybe people should start by trying to load the notebooks. I expect some of you have done this. So you should have access to the instructions that Nate sent around. I'm going to type in what you need to do anyway on the screen. Yeah, basically you need to type in micboop/ML decoders. And then, yeah, thanks, Georgia. Then I would recommend opening in a new tab so that especially when we open the later notebooks, we don't lose the first one. So I'm going to do that now. Yeah, so yeah, please let us know if you have any problems. Otherwise, you can begin by running the first 3 cells. So you just press the big play icon. This is going to install the necessary dependencies. It's going to download the data, which might take several minutes. It's going to import some packages as well. Yeah, and I promise I'm not installing malware on your computer or anything. Okay, so the download can vary depending on the machine that Colab assigned to you. Mine's going quite fast this time. But perhaps if you run that cell, we can go through the introduction matter. So we're going to use dataset 1, which I mentioned in the talk. So we had 13 participants. We sat them down for 40 minutes and played audiobooks at them. So there was clean speech in English. All of the participants were native English speakers. And there were 15 trials. So each trial was around 2.5 minutes, I think, of audio data. So yeah, there was no speaker 2 in this diagram. There was just one speaker, a happy participant, and then we acquired their EEG simultaneously. So if you want a snippet of the audiobook, it sounds like this. This was from the first trial, I believe.
Frederick Flushington belonged to a small college, and in doing so conferred upon it one of the few distinctions it could boast, namely that.
So Frank asks, how many trials? So there were 15 audiobook chapters, and each chapter was a trial. So yeah, this is the essential thing we're trying to do. You're welcome. We can study which features of the stimulus are encoded in the EEG by attempting to reconstruct them. So here's this typical diagram that I used before of using a linear function to move from the EEG recordings to the speech envelope. And then, yeah, you can correlate your reconstructions against the actual speech envelope and get these distributions of reconstruction scores. In this case, this box plot is actually for each of the 13 participants, I believe. And then we made an estimate of the null reconstruction score, which we'll discuss a few ways of doing it and maybe their pros and cons in the next two notebooks. Okay. And
so
yeah.
there are 13 participants, and Frank is asking how many trials?
Yeah, so there were 13 participants and 15 trials. 15
Okay,
chapters.
thanks.
So like lots of other studies, we asked the participants comprehension questions in between the trials. We didn't use that data, but it encourages them to pay attention during the next one and not kind of drift off if they feel like they're being tested. So just to get a feel for what the speech envelope looks like, we can plot it. At least this is a low pass filtered speech envelope. You can see it's basically tracking the amplitude of the speech waveform. And what's been shown many times is that this is quite strongly represented in cortical activity. And you can even see it with EEG. So it's, yeah, good feature. So you've probably seen quite a lot of ridge regression by now. The idea here being we take a section of EEG responses. So maybe 400, in this case, we used 400 milliseconds of EEG responses, which is about the length of the typical TRF we look at. And we use those to predict the speech envelope at the start of this 400 millisecond window. We do it that way around because we're assuming that the speech envelope caused the EEG to happen. And yeah, so there are various linear models you can choose. Maybe CCA would have been a good comparison, as Giovanni mentioned. In this case, we just used ridge regression, which has this classic formula. So yeah, we're going to look at tuning lambda and yeah, fitting these parameters, theta. So I hope everyone's getting on okay with installing the dependencies and downloading the data. I think mine's finished. So I'm going to move on. If you find you're falling behind or have some technical issue, please let me know. Awesome, thanks. Okay, so yeah, this is basically a recap. There were 13 participants, 15 trials. You can look at Hugo's paper, which is about surprisal in speech. So how surprising words were and how those surprisal values were encoded in the EEG. That's so Hugo, some issues with MNE. Yeah, Hugo did that study and that's where this data came from. Yeah, so as Giovanni mentioned, there are issues with sharing pre-processed data. We have shared pre-processed data. We would like to share raw data. I expect it would be possible to share that with you directly. Hopefully we can arrange to put it more publicly in the future anyway. Same goes for the other data set. Yeah, so we can plot some data. So the purpose of this cell is just to demonstrate that it was already pre-processed. So the EEG has been filtered between 0.5 and 8 Hertz. And yeah, the speech envelope was broadband, so it goes up to 50 Hertz. The sampling rate we used was 125 Hertz. Yeah, so that's, yeah, that number will come up a lot in the notebooks. So that's what it means. Yeah, so I said we're going to fit some linear models. So yeah. Yeah, just monitoring what's going on in the chat. If all's going okay, feel free to run this section, fitting a linear model for a single participant. Shouldn't take too long. And yeah, if anybody else is experiencing difficulties, please let us know. So yeah, in the paper and in the notebooks, we forewent the cross-validation simply because the DNNs take so long to fit and we had quite a large amount of data anyway. Some other studies have used a kind of shuffling thing. I guess bootstrapping is what they used, or some variation on cross-validation. We felt it wasn't really necessary. And certainly here we won't do it for time purposes as well. Good. Yeah, so this spits out some numbers. So to walk you through the code, we gave the ridge regression several regularization parameters. So these were spaced evenly between 10 to the minus 7 and 10 to the 7 inclusive. We split the data into a training section, a validation section, and a testing section. In the paper, we used 9 of the trials to train the models. It turns out Colab isn't super quick, especially when we use 9 trials, so we just used 3 here. And in this case, we're just fitting a linear model for the first participant. We're counting from 0. So yeah, the numbers that you see getting spat out, these tell you what we found the best regularization parameters to be, and what the test score was with that regularization parameter. You can also plot the validation curve, so how well each regularization parameter worked on the validation data set. And yeah, you get this characteristic shape for backward models where the validation score isn't so good when you have a small regularization parameter, and it isn't so good when you have a large regularization parameter. And actually, one of the exercises at the end is to discuss why that happened. So maybe have a think and we can discuss it. Yeah, so I hope by now that section's run for everybody. I can move on to the second section. Again, Colab happens to be a bit slower than my PC at college. So we're running this for 5 participants, just so it doesn't take forever. We'll be able to use data from all 13 participants at the end, just because I've uploaded it for you. Yeah, so yeah, maybe I should break this down a bit. Essentially, we've put this code we use to train the models inside a big loop. Yeah, we do the fitting of the model for all of the regularization parameters. This model selection function, this selects the best one based on the validation data set. And then I'm actually saving the model. It turns out we don't use it later, so this wasn't exactly necessary. But if you wanted to, that's how you do it. And then we evaluated the model in the test data set. And we're saving that correlation coefficient in an array. I've also included this calculation of the null correlation. We will discuss the cons of this method later, but to get a flavor of what's a random correlation, we correlated the predictions against the reverse of the speech envelope. We expect those 2 things should be unrelated. And that should give us an estimate of what the noise level or the variability in the reconstruction score should be.
So Giovanni was asking a question about the validation set. How large is it? If you can recap a bit.
I found it.
You found,
sorry,
okay.
later I found the line 9 to 12. Sarah is having a problem there, Georgia.
Okay, let me to help her.
Sarah, how did were you able to download the data using this cell? So did you see these outputs? I guess an alternative check.
I saw the outputs, yes. I think I do have them.
And do you see data.h5 in, if you press this folder button, I've messed everything up now, there we go. If you press this folder button and click on ML decoders, you should see data.h5 in that folder. Do you see that?
I think I have it on the other side for some reason. Okay, so what? I'm a bit lost. I don't think I have the same configuration for some reason.
Okay.
No worries.
Wait, so did you launch the notebook by going through this screen?
Yeah. Wait. Oh. Yes.
Yes. Okay. And you ran the cells in order?
Yeah, it should be. I can try from the start and see what happens. Maybe I reran something by mistake.
Okay.
It's possible.
I'd recommend if you go to runtime and restart runtime, just so we start with a blank sheet.
Okay.
Yeah.
I think it's also better make a copy of the notebook.
Oh.
I mean, copy to Drive and then just start working from there, and you can also do changes and everything.
All right. I will try to figure it out. Thanks.
Okay. Yeah, I'll check in a in a few minutes. Yeah, so this is still fitting for me. Yeah, it's almost done. It's done 4 out of the 5. But yeah, this is basically why we didn't run all 13.
While we wait, Michael, I can't find it. What's the high pass filter here?
For the EEG?
Yeah.
0.5 hertz. So we had a look at different high pass filter cutoffs, I guess. And yeah, out of the ones we looked at, that was the best. So I know people have reported using 2 hertz before. We found that wasn't great. But then also the reporting of what filters people used isn't necessarily always good. So it's hard for me to make a comparison based on that.
Yeah, it always depends on the method and what you're trying to do. But what kind of filter do you use?
It was a Hamming window.
Okay.
It was basically the default of what MNE does. Yeah, so yeah, it's an interesting point because of course we said the latency of the decoder is like 2 seconds or whatever, but of course you also have to filter the data, and you can definitely choose better filters for doing that if you want a fast decoder.
Yeah, you know, one thing that Alan taught me there was always to estimate the response of the filter. So to calculate the response of the filter and, you know, plot it beside your TRF in a way.
Okay.
Because sometimes, you know, the filter may have the shape of a TRF. And if the order, I mean, I'm talking about infinite response there. If the order is high enough, then the latency may be high enough, and then, you know, it's going to impact, of course. But I don't know how it is with Hamming windows now. But anyway, it's beyond the point. Sorry. Is it going to, sorry?
Yeah, I had another thought and I forgot what it was. Yeah, that was it. I guess the technical point that was something of a mistake on my part was my outputs have a much broader frequency band than the inputs. And in general, this isn't great practice for linear models. So when you do a linear model, the outputs of the linear model can only contain frequencies that were in the inputs. You find that if you look at it in the Fourier domain. So that probably increases instabilities and things. If I was doing a TRF, it would look really spiky if I did that. Okay, so my code is run. So I'm going to move on to the next couple of cells. Where, yeah, we look at these correlations for the 5 participants. So this was the trial-wise, well, I guess, the correlation over the 3 test trials. And then in orange, this is the correlation of the reconstructions with the time-reversed speech envelope. And yeah, I made this claim that there should be no systematic correlation between the predicted speech envelope and the time-reversed speech envelope. We'll find later that whilst that's true, there can be a chance correlation and that can bias your null distribution. So this is kind of a quick and dirty way of estimating the null distribution, but actually for a publication or something, you should consider something that doesn't necessarily have a biased tendency. So in the next notebook, I'll show you all my null reconstruction scores are like negative or something, and that doesn't necessarily look very null. So. Yeah, the last part is just, if you like, you can do a t-test between the correlations and the null correlations. T-test is normally okay because the correlations aren't so big, and they tend to look quite Gaussian distributed, normally distributed. What does a negative correlation mean? As in, so when I said negative correlation, I meant this Pearson's correlation coefficient is coming out as negative. Is that what you wanted for an answer? Or do you want a kind of explanation of why the correlation was negative?
I suppose one comment I have there on the time reversed envelope, if I can, is that, you know, what may be missing there is also to do the correlation between the envelope and the time reversed envelope in the stimulus domain. And there you can check, oh, okay, is by chance that particular, because if this was music, then it would be different. Because then the tempo, maybe, the tempo is the same, and so you catch some correlations that should not be there.
Yeah, so when you do that with this data, you do in fact get a spurious correlation of like negative 0.05. And this is why these null scores tend to come out as negative, although they're not that high. So like a future method, I think we do it in Notebook 2. A different way you can obtain these null distributions is when you do this dividing the data into windows, you can correlate the reconstruction with the actual speech envelope from a different window. And you expect these different windows to have different spurious correlations which cancel out. And yeah, that's what we did in the paper, and that's why we get 0 as the median null score. But yeah, that was a good point. That'll explain the result we see in a bit. Yeah, maybe people can put in the chat how things have gone. Are we still waiting for things to run? Any questions? Are we waiting to move on to the exercises?
We have some feedback in the chat. Seems that everything is going fine.
Okay.
So everyone is doing well. Don't be shy. Just raise your hands if you feel you're behind, or type or post your question in the chat, and I will ask it to Michael. Okay. So I think we can move on.
Okay. So the next section is to find the regularization curves for several of the participants. So basically the purpose of this exercise is to ascertain whether this is a characteristic shape or whether this looks quite different for each of the participants. And we really should, I really should have saved the validation scores when we ran this the first time. But effectively, to do this, I've basically saved the validation scores. So remember, this is the data that I plotted here. And then, yeah, so that's going to run, running it up here. But we can move on to the second one whilst that's running, if you like. Maybe I'll just give you like 20 seconds. Can I repeat that? Okay. So yeah, this exercise is about obtaining these curves for several of the participants. So basically we need to do this procedure and save what's called the validation scores. And it's because we start with this cell. Validation scores contains the correlation coefficient for each regularization parameter. So basically we need to save this variable for each of the 5 participants that we're looking at. Does that make sense? And then if that makes sense, then I can show you the modification I made to the code.
Yes, please. Yeah, yeah, makes sense. Yeah.
Okay, awesome. So yeah, the modification I made to the code was I just created an array where I'm going to dump these outputs, and I did that with this line. I was going to call it val scores, but then I'd have a naming conflict, which is why it's called all val scores. So yeah, these are just getting appended to that array. Okay, so maybe we move on to the last part of the second exercise whilst that's running. So I guess maybe someone wants to volunteer. Does anyone have any idea why the validation score is so low when the regularization, yep, sure. When the regularization parameter is so low?
So there are some people in the chat asking for you to show again the modification you did, where you save all the validation scores.
So yeah, I think I should have saved these the first time around. That's okay. Yeah, so basically the idea is you add those 2 lines and then you run the cell again. And yeah, for me, this is on the final participant. Don't worry if yours is going a bit slower, or if you started later, that's fine. Yeah, maybe I'll show you that. Cool, thanks, Frank.
So here it's not clear to me, you're choosing the best lambda for each of the participants, right?
Yes.
Okay.
Yeah, that's subsumed into this model selection function. So yeah, this ridge function or class, this was, if you watched Giovanni's talk yesterday, this was some custom lab code, which I hacked a bit. So
So it basically directly returns you the best the model with the best lambda or something.
So it gives these validation scores.
It gives you the validation score.
And these are the validation score for every regularization parameter.
Okay.
The other thing, yeah, the other thing this function does is it updates. It has an internal state which says what the best regularization parameter is.
Okay, I see. That's why I don't see the selection, right?
Yes.
Okay, okay, that was my question. Yeah.
And then it uses that parameter automatically when we do the testing.
Okay, perfect. So then when you use it for training, it automatically uses the best lambda, which was chosen during cross-validation.
Yes.
So the differences with MTRF cross-val is that there you get the lambda as an output, and then you train with that lambda. Here, everything is internal, so we don't see it, but it's there.
Yeah. So yeah, I guess the purpose of this repository was more to showcase the DNN. So yeah, I would recommend if you want to do more TRFs, I would use a good TRF package like MTRF Toolbox.
It was not a critic. It was just for me to understand the procedure here, because it was not clear to me where was the selection of the lambda.
Yeah, I agree. It raises the point though that it's not great practice to hide loads of stuff from the user. But yeah, I mean, the DNNs is maybe less hidden. Okay.
There is another question in the chat. Anna is asking, can you explain what the ridge function does?
Okay. So I'm not sure if you saw the some of the previous talks, but in a nutshell, it's an algorithm. Ridge regression is an algorithm for fitting a linear model. In this case, we have multivariate inputs. So we have each EEG channel, of which there were 64 electrodes, but they were referenced. So there are 63. 63. Sorry, I'm watching the chat. There were 63 channels, and then for each channel, we also had several lags. I hope that makes sense from the talks before. So we had 50 lags, which are 125 hertz, corresponds to about 400 milliseconds. And then we had 63 channels. So you have quite a high dimensional input space. And then we're taking a linear combination of all those numbers and trying to turn them into the speech envelope. And it turns out the parameters of that model, when you do ridge regression, which depends on this parameter lambda, the parameters come out or are go according to this expression. Are you?
I think she was referring more to your implementation. So the function ridge, which is the cross-validation function.
Yeah.
Okay, so yeah, it was not clear also for me, but okay, I think she was mentioning the function.
Okay. So Mel asks about changing the number of trials. You don't actually have to change anything because there are already 3 trials being used to train the model. But if you want to see where it's defined, that's what this cell is all about. So this says train parts, the word part instead of trial, but it's saying which ones are going into the training data set, which ones are going into the validation data set, which ones are going into the test data set. Yeah, I'd like to add as well, it's not doing cross-validation in the same way that you, I don't know, the normal way in which you choose which part's your test part, and then you iterate that. We just have a fixed test section, a fixed validation section, and a fixed train section. Okay, so hopefully this cell where you're collecting the validation scores is running. I will plot mine. Awesome. And it works. Okay. I would add, we are doing quite well for time. The last notebook is pretty speedy. Okay, we're not going to do that. Okay, so yeah, these are the regularization curves for those 5 participants. So I plotted the results we got from the loop that we modified, and the x-coordinate is the regularization parameters that we chose, shown here. And it's on a log scale so that we can actually see what the curves look like. So yeah, maybe we discuss the first 2 points. It's fairly clear that this optimal parameter is quite different for all the participants. And you can calculate the mean and stuff if you like. I think maybe the most important thing is about the small and large values. So does anyone have any idea why the performance is so small when the regularization parameter is so small? Giovanni and Georgia are also welcome to answer.
I'm not sure, honestly. And thinking about that.
Right, because it looks different. If I remember correctly, it looks different for forward models, right? It doesn't drop off that much.
Yeah, with forward models, usually very small values, it stops changing when you go below a certain threshold. This is backward model, you say. Is it a trick that you put in the code, or is it a more general theoretical question?
It was a more general question. I mean, it's always possible that it's to do with how I thought and stuff, but my explanation is that there's a lot of collinearity in the inputs we're passing to the ridge regression. For example, we low pass filtered the data below 8 Hertz, but we're still sampling at 125 Hertz. So for instance, neighboring time samples are going to be highly correlated. Also between channels, you get correlations. And basically, if you imagine setting this lambda term to 0, what you end up with is a matrix inversion, which is quite unstable if you have collinearity. And it might not generalize that well. Like you might attribute the information to the wrong thing.
Still going down to 0 is a bit extreme, all right?
I believe this is consistent with, did you see, there was a paper, it was like different regularization methods for encoding and decoding models.
Sorry, you mean Joshua's?
No, it was, I can't actually remember whose paper it is. It's
I don't remember, but I mean, it could be absolutely. I don't have that much experience with backward models, but do you think it's more of the temporal correlation or the spatial? Like if you run this on just one electrode, what happens?
Good question. I haven't done it. I'm not actually sure. I suspect it looks similar just because we used a high sample rate relative to 8 Hertz. Yeah.
Oh, yeah, of course.
I think their conclusions were like, it matters more for backward models than forward models. Yeah, so when they used ordinary least squares for, I guess this is attention decoding, they got a much lower score. Probably shouldn't be. It doesn't look like this comes from a 0 reconstruction score, but I guess I can't tell from the data. Basically regularizing had a massive impact in the backward model.
Yeah, it is also true. I mean, I've always seen massive lambdas in backward models compared to forward models. Like, you know, at least 100, 1,000 times larger. I've always thought it was because anyway, you have many electrodes and so you have many features. I never really thought too much about that, but so you're saying it's because of the instability that comes, that instability matters more in backward models. It makes sense.
Yeah, well, I know this is why this lambda term was introduced. That kind of preceded this shrinkage idea. The idea was just to stabilize this inversion when you have collinearity.
I know what you mean. Just in forward models, prediction doesn't go down to 0. For forward models, it just stays up. You know, the TRF looks weird because you get all of these spikes that you know you can't really interpret, but the predictions are not necessarily terrible. But anyway, I don't want to hold you up now. It's interesting.
Well, yeah, I mean, maybe just briefly. I think it makes sense because in the forward models, you would aim to have a wider frequency band in your inputs, which is the speech, than the outputs, and therefore there would be less, I would expect, I'm kind of making it up to be honest, but I would expect less collinearity between neighboring samples than if I had so aggressively filtered them. And of course there are less channels, like you say.
Yeah. And just one addition that I'd like to tell you since you're here. I've never done it, but one could potentially start thinking about using the optimal lambda as a result as well, like because it tells you something about the data. I've never done it though. Like usually I just optimize and use that, but in reality is that you have certain subjects are more regularized than others. just put them together, but it also tells you something about the data, what optimal lambda you're using. So it could be interesting information. Anyway, sorry. Looking forward to the DNN part.
Oh yeah, let's do that. 650. Okay, I think that's
we
okay.
just check really quickly the second question. So you have the result of the lambdas. We will get the mean. I get the mean. But would you apply then this lambda mean to all the participants? Or this is a Homer Simpson question? Or you will keep always a lambda for every participant? For example, now the mean will be like 0.07 something.
Yeah,
or it was just a question for the exercise?
It was just a question for the exercise.
Okay,
So it's like you could look at, here's the mean, but actually for this participant, the best one is miles away or something like that.
Okay.
Yeah, and actually, that was the point of the first question, was that for these subject-specific models, it's advantageous to use their own regularization parameter. And yeah, that will be revisited in the second notebook. So yeah, in the second notebook, we can go back to this page. So colab.research.google.com, just in the chat at the top, I think, as is Mike Boop, ML decoders, and then you can just open the second notebook in a new tab. So I will do that. Please let us know if you can't find it or if you're struggling with something like that. I'm just going to go ahead and reset up the notebook. This is the last time we have to do this, so that's good. At least the last time we have to download the data. And I've done it wrong already, sorry. Okay, so I should have read my own instructions. It says, please enable hardware acceleration for this notebook. So that can stop, please stop. The way we do this is we go to runtime, change runtime type. And it says GPU. And now this means we can do calculations on the GPU. And Colab's good because it provides free GPUs, which you can use like this. GPUs are good because they can parallelize matrix operations and make that stuff happen a lot quicker. And that's useful for DNNs, which typically involve a lot of smaller, relatively matrix operations. And if you only like partly parallelized it, it would take forever. If you did it sequentially, it would definitely take forever. Yeah, so now I'm going to run these cells again. And this cell isn't going to complain at me this time because we're using the GPU.
I use so much the GPU this morning that I cannot use it anymore. That's the only problem. I will follow just the
oh no, I'm sorry.
your computer. Yeah.
I've never heard of that.
Yeah, because you have an amount of time that you can connect, I don't know how many times in a day or something. Yeah.
Ah, okay. Now would be a bad time for that to kick in. Okay, so yeah, maybe we can go through the intro matter whilst that happens. Yeah, sometimes you get a better machine with better, faster hardware, and sometimes it also has a better internet connection for some reason, but that's okay. Yeah, deep neural networks. The essential idea that I need to go away with is that they have lots of parameters and they're nonlinear. And in fact, they can represent many functions, so they're very flexible. Yeah, it's almost always going to be impossible to solve them closed form like we could for ridge regression, so we can use gradient descent instead. So we're going to be using the PyTorch library, which has, it implements everything. So it implements gradient descent. It implements the building blocks of the DNNs, and it makes things nice and easy. And there are many tutorials out there for PyTorch. If you're interested in some specifics that occur in the code, I'm happy to address those questions. Yeah, I mean, a comprehensive introduction to PyTorch would take a while, take as long as this tutorial probably. Yeah, so we can, if you like, we could compare this top DNN to the linear regression that we were doing before. And basically the idea is that in linear regression, we had all these inputs shown on the flattened column, and we formed a linear combination. And that was our prediction of the speech envelope. So this linear combination is represented by these faint lines. So if there was just one node here, we'd effectively have a linear model. Yeah, so the fact that we have stacked loads, and crucially, we do a non-linear function, so maybe we compress the outputs of each node, that's what makes it different to linear regression, and that's what makes these things quite powerful. It seems kind of arbitrary, but that's what some clever maths people have done to show that to find something which can approximate many functions, basically. Yeah, so there are loads of approximation theorems. I don't really know the specifics of them, but yeah. Okay, my data is downloaded. That's good. Yeah, again, let us know if you have problems with that stage. If the data is not appearing here, something's gone wrong. So, okay.
I have a question, if I may. It regards the architectures you choose. So it's more about the difference between the two of them. So I know that with the FCNN, you wanted to choose the simplest architecture possible, right? You said so in the talk. And then you choose a simple CNN, right? But the two of them, they are intrinsically different in the sense that the CNN basically will treat the EEG signal as an image because of the convolutions, right? So my question is, the EEG signal is not an image. So the relationship between time samples is not the same relationship between channels. It's not as in an image where the pixels, I mean, there is this symmetry between the two dimensions, right? So I was wondering, what's your thought on that? Because for EEG, it's quite hard to find the proper architecture.
So, yeah, I mean, I guess several thoughts. Firstly, as you say, maybe if I can rephrase it slightly, if you were comparing neighboring channels, you could change the order in which you put these next to each other, which you align them, and you might end up with a different answer. So to avoid that problem, we only do the convolution along the time dimension. And actually, in this stage, we just take linear combinations of the channels. We take several. So it's like a projection to a different space, basically. But then we reduce the dimensions. So we.
Okay, I see. Thank you.
Maybe two additional comments. Firstly, I'm not sure how crazy you should go with this, at least for envelope responses or envelope decoding, just because I'm not sure how non-linear it is from EEG. So there was a forward modeling study, and I'm not exactly sure how they got the figure, but they said approximately 25% of the evoked response arises due to non-linearities. And like, essentially they did a neural network and they presented it with different kinds of stimulus, like different clicks and stuff once they trained it on the envelope of the EEG. And they said, this is how much more activation we get in the impulse response. So yeah, I'm inclined to not do snazzier things. But if you did want to explore the relationships between the channels and stuff, you could do things like placing them on a graph. So seeing which channels at a particular latency are similar to other channels at a different latency. And then graph convolutional networks are kind of popular right now. Yeah, I mean, I feel like I'm not going to do that. But you may find, it's kind of the annoying thing about this stuff, you may find it does work better. My feeling is that it won't, but yeah, you never know until you try it. Okay, in this case, I am going to use all 9 trials for training the DNN. This is because we needed that amount of data to get a good fit. It simply didn't work if we used 3. But as we'll all each be training 1 DNN for a participant, so it shouldn't take as long as waiting for the linear models to fit 5 participants or however many. So someone raised the point about using average hyperparameters earlier. So these DNNs depend on a number of hyperparameters, which I can go through, but maybe we do it later. And essentially, it takes ages if you try and do a massive search of all the possible hyperparameters, and especially if you try and do this for all 13 participants. So I determined these hyperparameters in a population average model. And then we use those hyperparameters for the subject-specific models. And then, yeah, basically, as we saw in the last notebook, that might not be the best approach. So we'll also go through tuning the learning rate parameter, which I can explain in a sec. We'll retune that parameter for each of the participants, but we won't do all of them just because that would take absolutely ages. Okay, so yeah, we can define those hyperparameters. Those are the ones we use in the paper. And then we can run the train DNN function. So the train DNN function needs to know where the data is. It needs to know which participant you want to use. This says participants because you could use data from multiple participants if you wanted, but we won't do that. Checkpoint path. This is just an option for saving the model intermittently. So your training might get interrupted for some reason. Say Colab says, you've used it for too long today and you can't do any more. The model handle, this is just saying which DNN we want to train. So I want to train the FCNN here. This is telling us the train validation split. Epochs. So sometimes I said this gradient descent algorithm was iterative. And what we tend to do is we tend to chop the data set up into what are called batches and descend the gradient. So approach the minimum, hopefully the global minimum, but you never know, using each of these batches. And sometimes you don't get there when you just look at the data set once. In fact, normally you don't. So the idea of epochs is you present the data set to the optimization algorithm, this gradient descent thing, multiple times, and you keep getting closer and closer. So I've said epochs is 20. That can take a while. So I've included this parameter called early stopping patience. And this basically says, if I don't increase the validation score, so the validation correlation coefficient, within 3 epochs, then I stop training because I don't think it's going to get any better. This is also a hyperparameter, but I didn't tune it because that would also take ages. Workers, it's just a compute thing saying how many CPUs do you want to deliver the data to the optimization. I don't really know how this stuff works under the hood, but when I tried to increase this number, Colab said don't do that. So we're going to use 2. yeah, if you had a more powerful machine, you could use more and it goes quicker. But it's not really a technical thing about DNNs. It's more about how PyTorch works. And then, yeah, we say which hyperparameters we want to use. I realize some of that may have been kind of quick. So feel free to ask if some of it seems mysterious.
I was wondering if you can comment a bit on how to build a data loader for this type of models, because that's something that people who are not working in deep learning maybe are not familiar with. And it's often very hidden in the codes in the sense that you don't see it here, but that's the biggest part of that's biggest work to do. Create the data loader, chop the signals, create the batches for training. I was wondering if you can quickly comment on this.
Sure.
Just to give a picture of how it is different from how we usually work.
Yeah, so firstly, what is a data set? I said this gradient descent algorithm, at least one of the sub flavors, stochastic gradient descent, splits your data set into batches, and then tries to descend the gradient, so approach the local optimum or the global optimum, preferably the global optimum, but you don't really get to choose, by looking at each of these batches of data. So this basically means you need to divide your data set into batches to present it to this algorithm. And there's a thing called a data loader in PyTorch, which does that for you. It's not super nice when you first see it. I think I've got it somewhere. Evaluation. Yeah, this data loader thing. This data loader splits your data set into batches. And then basically you can write a for loop which iterates over the data loader. So on each iteration, the data loader spits out the next batch of data. So in terms of making the data loader, you need to pass it a data set. And this is what I found kind of confusing when I started. The data set is the thing that you need to spend the time constructing. So data set says, it has some methods. It's basically a class, which is a thing in Python, which you probably don't use as much in MATLAB. But it basically tells, it has several methods or functions it needs to implement. So it has a get function. So it says, given a number, an index like 10, get me the 10th entry in the data set. It has a length. So it tells you how many, effectively it works out how many batches are going to be in the data set. And those are the two methods.
There, right, that you define the length of the segment and all of these parameters, right?
Wait, so you define the batch size. So this is how many.
You define the batch size, okay.
I can't remember why I needed the length attribute. It may just be required, but the length says how many samples are in the whole data set.
Yeah, I think the length is needed for PyTorch, but what I was asking is that all the operations we need to make on the data, on our data, like segmenting the data like in 2 seconds length segments, is that something we need to do in the data loader?
So,
or not necessarily?
The data loader, yeah, that divides it into batches. For evaluation, I also use the data loader, and that, because it automatically divides it into 2 seconds, or however many seconds you want. In terms of other operations, that was something I did in the dataset stage. So I standardized the EEG channels. So they had zero mean, the same variance. This actually ended up being really important because different people have different power in their EEG. And when you throw that into a nonlinear thing like a DNN, then suddenly you find it doesn't generalize between participants very well.
Okay, thank you very much. And I think you have another question in the chat about LSTM. So, yes, Judith saw a talk where they were using LSTM for EEG data and auditory stimuli. And she was wondering what you think, if you have any thoughts about this choice.
Yeah, I think I tried a LSTM and I found it hard to fit. That was my experience. Then I'm not super experienced with them. We were gonna try. I want to try loads of things, but there was discussion of trying something similar. It's kind of it's like an LSTM, but it has some notion of how noisy the data is, and that may end up giving you a better fit. But yeah, the LSTM, I'm not sure. This is the thing. I couldn't get it to work when I tried. I didn't have the most comprehensive effort, but whereas I said I wasn't convinced that trying really snazzy feed-forward architectures would help, I think there's definitely a lot of scope to explore how memory might help you do this decoding thing, especially because the EEG itself is quite an interesting structure in it across different timescales. It could well be interesting to see how the LSTM works if you can get a good fit.
Okay, thank you very much.
Okay, this is stopped. So I've trained a DNN. Yours is still running. Okay. Did you all change to GPU? It could just be that you have slower hardware as well. So you don't get to choose on Colab, I don't think. I guess it might be important to figure out, are you all still on like the third iteration or the first iteration, or are you somewhere down here? Because if it's running so slow that you're still here, that's a problem, I think. First, are you the person who's using CPU? Nope. Okay. Okay, this might end up being a problem. Okay. Has it printed out the first number? Third here, okay. Cool. Okay, I'm gonna carry on. I'm hoping it's just a couple who are having this issue, in which case it's possible that you've just got some poor hardware from Colab. Yeah, I'm not really sure what to suggest other than if it's going much slower than mine was, you could try reloading the notebook. Obviously that'll take a while. So yeah, you're welcome to try that. That's kind of my only suggestion. Yeah, I wanted to quickly comment on this part. So each number here is the validation score after we went through the entire train data set. And we said we would do this a maximum of 20 times. That's what this parameter means. 8, 9, 10, 11. And we only did it 16 times. And basically this is what's called the early stopping kicking in. So we found a high relatively validation score here. And then it didn't increase for the next 3 epochs. And the algorithm has decided that if it hasn't increased within the next 3 epochs, it's not going to increase at all. So then it terminates the training. And this is a pretty simple, I guess, pruning scheme. There are others you can choose. I didn't feel it was warranted as we weren't doing massive models. But there are lots of suggestions people have about when you train multiple models over different GPUs, when do you stop them if you track their progress at the same time? And it can get quite complicated. But yeah, we just used early stopping patients and it worked fine. So that's good.
Sorry, what's the validation metric here?
This is also the correlation coefficient.
That's the correlation. So, okay, the higher the better. Okay.
Yes. Okay. So now we can.
Okay. So sorry to ask, what's the loss function you're using for training?
Yeah, that's a good question. I used, so PyTorch always wants you to minimize something. So I minimized the negative correlation coefficient.
Okay, I see, okay.
So yeah, this maximizes the correlation coefficient, which is what we
want. Maximizing sounds weird.
Yeah, okay. I found the first time I saw this, so this was inspired by the Taye paper who did this kind of thing first. At first I thought it was a bit of a weird thing to do because obviously the correlation coefficient doesn't care about the scale of what you put into it. So you would think there would be multiple solutions. But basically the non-linearities in this DNN, so these functions, so particularly compressive ones, these have a characteristic scale, which I think controls for that. And also this weight decay parameter is very similar to the regularization parameter in ridge regression, and that also shrinks the coefficients. So they have a characteristic scale. So this is why it's a stable thing to optimize. I don't think by itself it is. Okay, so I'm going to carry on to evaluation. So this train DNN function spat out validation accuracy, which should be this number here. It's the best validation score over all the epochs. And it also spits out state dict, which is a dictionary in Python. One of the things it contains is the best model parameters. So we need this to basically save the best model parameters so that we can use them later. And this code cell tells you how to load a state dict. So yeah, you create an instance of the DNN, and then in PyTorch you use this method load state dict to load the parameters into the model. This is a useful object because you can save it and, I don't know, email it to yourself or train something else using these initialized weights. So that's why this is a thing that you can have by itself. Okay, so yeah, these are the dataset and data loader objects, which I mentioned before. So yeah, I've created a test loader, which is dividing the dataset into 512. Okay, yeah, 512 sample windows. I'm then gonna, this isn't 2 seconds, but I'm then gonna stack all the predictions on top of each other so that I can compare using multiple windows. So yeah, test loader basically is saying, I'm going to divide the data set up into windows. There's this batch size of 512. I use a small window because I want to do this on the GPU to make things go faster. And then at the end, when I have all these predictions, I'm going to put them back together so that I have the predicted time series. Does that make sense? Maybe it wasn't the clearest explanation. Essentially, the idea is that I need to use a data loader to access the test data. This batch size parameter doesn't matter too much. I'm just going to use this function to obtain the predicted time series. So
I'm sorry. Just to recap, the train function is training a model for each subject or a model for all the subjects together?
Okay.
Is it subject independent?
This is subject specific.
Okay. It's just that we don't see it because the training function is taking care of it.
Yes.
Okay, so we don't see the for loop over the participants because it's inside there. Okay.
Yeah, I think that's
parallelized things, or I don't know.
That's okay here. Because I mean, this is quite a common thing because training functions end up being quite long. So I've explained, I've stated in the function call what I want to do. So I want to use the participant which is saved in this variable. So there's one participant we're using.
So it can be only one participant at a time, or you can. Okay, so it was participant 0. Okay, I see.
If I wanted to do.
Yeah. You can do this.
You can. Yeah. I left that part out because, of course, that takes longer.
And then you get a model for each of the participants.
Then you get a model that was trained on all of those participants. So.
Okay. Okay, I see. Okay.
Cool.
Okay, that's clear now. Thank you.
Yeah, this is subject. Yeah, Fatima says this is subject specific. So yeah, basically you need to run this cell to obtain the outputs of the DNNs on the test set. So we give the test data set in the form of this test data loader. We give it the trained model and we ask it to do it on the GPU so that it goes quickly enough. And then we can compute the correlation coefficient between the speech envelope and the predictions. And in this case, we find something around 0.2. Okay, how are we doing this stage? Do we have questions? Some of this was kind of, I feel like we're sitting between kind of what do the DNNs do and how does PyTorch do stuff. So yeah, if that's being a bit confusing, please ask.
That's cool, Michael. And I mean, the numbers go up compared to what I'm used to see anyway. So that's great. Does that correspond to an increase in, if you know, in decoding correlation in terms of attention decoding? I think that's what you showed before, right? So the correlation goes up, and also you get Because I would imagine that in a cocktail party scenario, you can get a better correlation for both the attended and the unattended speech, for example.
Yeah, so that's in fact not what we found. Of course, it's a possibility. It was a possibility before we did it. So the original study by Detaille essentially said it was doing the same thing, but there was a big focus on what the attention decoding accuracy was, and we didn't see what was happening with the envelopes. So when we looked at, this is why we used different listening conditions, so different noise conditions and stuff, but we could also see what was happening with the unattended speaker and the attended speaker. And essentially in our training data, only a single speaker plus maybe speech-shaped noise was used in that data set. And this is probably why the unattended speaker reconstruction wasn't boosted. So obviously it'd be a kind of an insane thing to do to mix the attended speech envelope and the unattended speech envelope in the targets. But if you had trained it to do the unattended speaker, I expect you would have seen a performance boost as well, right? Okay, how are we doing for time? 7:30. Okay, so we can try and do the same thing that we did before. We can try and come up with something that's like a null reconstruction score. And remember how we did this previously was we reversed the actual speech envelope and correlated it with our unreversed predictions. So that's how you compute the null reconstruction score in this case as well. In this case, I have to shave off the last 50 samples of the speech envelope. This is because of the receptive fields of the DNNs, which is 50 samples long. For the linear regression that we did in the previous notebook, I zero padded it to make them the same length. There was an option to not do that, but there was no option to do that here. By the way, if you're not familiar with Python, this kind of weird notation means reverse the array. This notation means give me everything up to the last 50th element. So this gives you the whole array except for the last 50. And then we can do that calculation, and we end up with something that's slightly negative but also small. So we don't really have enough data to do a hypothesis test, but it looks like the null reconstruction score is looking quite different to the actual reconstruction score. Okay, how are people getting on? Is everyone happy? Are we still running things? Okay. God, oh, I'm sorry. Yeah, if you wanted to, you should be able to run this whole notebook by pressing run all. So if you wanted to do it at a different time, when hopefully Colab gives you a better PC, you're obviously free to do that. Okay. This cell is going to show you how to tune the learning rate parameter. So the learning rate effectively tells you how quickly to descend this loss function. If you're familiar with DNNs, I guess that'll make sense to you. If you're not, I can try and show you the picture from the presentation. Maybe not. Okay, sorry, my PowerPoint is not working. Effectively, the gradient descent algorithm is iterative. So you start with some random weights, and then you try to make the weights better to increase the correlation coefficient. And that is what we call a gradient descent step. And this learning rate says how different can the new weights be to the previous weights. So effectively says how far can I travel from where I started in one iteration. And there's a trade-off with this parameter. So if you use a large learning rate, then you'd think you could arrive at the optimum more quickly because you can update, you can change these weights more quickly. However, you may miss narrow optimum in your optimization surface if you use too much of a learning rate, too large of a learning rate, because you're basically stepping over them. But if you use a learning rate that's too small, you may fall into local optimum when you actually want to step over them and arrive in the hopefully wider global optimum. So basically, this is a parameter that needs to be tuned, and it's probably going to be subject specific, as are many of the parameters, but perhaps this one more than others, just because the noise level in different people's EEG may be different, for example. So the first thing we do is we get rid of the old learning rate. And this is the optuner section. So please stop me if I'm going too quickly. Essentially, before, what we did was in the linear models, we trained a linear model with each of the different regularization parameters. This was a different form of hyperparameter tuning. We're going to do the same thing here. We're basically going to train the model using several learning rates that we defined at the start, and then we're going to pick the best one. And this is called doing a grid search. So the way optuner works is it wants you to have an objective function which you maximize with respect to the parameter. So if this is ridge regression, the parameter would be the regularization parameter. Here, the parameter is going to be the learning rate. So this is that objective function which returns the best validation accuracy for that learning rate. And then we create a grid sampler. So this defines what's called a grid. In this case, it's an array of hyperparameters. So this is where we define what the candidate learning rates are going to be. And then we're going to find out which one of these works the best. We then create a study. So a study has a lot of functions which we're not going to use, but it allows you to track what's going on inside this optimization procedure more closely. This is just part of how optuner works. And then using this study, we can just ask it to optimize the objective function. So how was that? How do people feel about that? Does that make sense? I'm trying to draw the parallel between ridge regression. So it's very similar to how we tuned that regularization parameter. The concept I want you to take away is that we're going to try out all of the learning rates and we're going to pick the best one. There are different schemes for choosing hyperparameters. In this case, as we're only looking at the learning rate, we can use a grid search and it's not too costly. Okay, so maybe to make that clear, we can just watch the outputs of this function. I only used 5 epochs this time, so whereas we used a maximum of 20 here, just to make things run kind of faster, I'm only using 5 for every learning rate. So we're going to see, we started by using this learning rate, 0.01. We've already gone through 4 epochs, so we're going to move on to the next one pretty soon. Yeah. So this is all within the optuner package. It's doing this optimization for us. So it's keeping track of which learning rate was the best. So at the end of each trial, a trial is when optuner looks at a specific learning rate and calculates the validation accuracy. It tells you what that validation accuracy was.
There is a question there in the chat from Judith. How do you pronounce your name, Judith or Judy? I'm not sure. First, she says, how do you determine which learning, oh, either works.
Either works.
How do you determine which learning rate range to test?
I used quite a large range, is the answer. I think it's kind of funny, but if you if you Google what's the best learning rate for deep learning, it's quite common to see people say 3 × 10⁻⁴, and that seems like a completely arbitrary number, and it is. So I did comment to a friend that was kind of arbitrary, and then when I did this procedure, I got 3 × 10⁻⁴, and that was really weird. But like, generally that is where I start, but if you kind of go a few hundred times smaller or a few hundred times bigger, you're probably going to capture, there's probably going to be something that works pretty well in that range. If you find, and that's what we found, if you find it's really not working at all, you can always increase the range, but like unfortunately there's no good rule for choosing how big or small you want these parameters to be. It's the same with all of these hyperparameters. Like, for example, the number of hidden layers you're going to use here, it can be really hard to tell. We used between 1 and 4, and we found the best number was 4. So maybe using even more is better. We didn't do that. In fact, it was similar with this. If you use less nodes in the CNN, you get a very similar score. So I wouldn't suggest that 3 × 10⁻⁴ is the holy grail, but I would. That is where I start, just because of what I've experienced. I think it's wrong to just pick a number and then roll with it. But I agree that picking a large range around that does tend to work, and that's why I did it. Yeah, I would say I started with 1 × 10⁻⁴, because I think it's kind of 3 × 10⁴ is a very specific number, right? Like, it's a yeah, I personally start with 1 × 10⁻⁴ and then use a wider range. And yeah, this stuff is kind of grim because yeah, thanks, Georgia. Yeah, that's important. Yeah. That is why the range is so large, is because we're on this log scale. I'd say it's more common to do what's called a random search, where you say, I want to find the best learning rate between 10 to the minus 6 and 10 to the minus 2. I'm going to give you 10 attempts to do this. For each attempt, you pick a random learning rate on a log scale between those two numbers, and you see what you get, rather than using this evenly spaced grid. Yeah, we didn't do that. I think we did use a random search for things like dropout and weight decay.
I think there is no specific rule also. I mean, if you talk with people using these neural networks all the time, they will just train, yeah, exactly like 5 learning rates. They will see if they are overfitting, so they will decrease, because also a really small learning rate will not, the neural network will learn nothing, basically, right? So it will be just like a linear fit. So you want to improve the accuracy. So I think at the end of the day, you just play around, and that's why this Optuna optimizer is really good, right? You just optimize the best that you have, but there is no science behind it. It's like an art. Just try and try and try, and once that you have a good parameter, then you just keep it. Yeah.
I agree. I think one thing that makes me quite uncomfortable about deep learning is the way it kind of normalizes trying something, looking at your test score, and then trying something else. So see if I can bring it up. This basically introduces a lot of bias into your analysis pipeline. So you can end up coming up with conclusions which don't generalize very easily when you do this. And there was a really cool study that I can share. Oh, yeah, that was... Yeah, so this in fact isn't just a deep learning thing, but if you say you collected some data for your experiment and you run many analyses on it, but you change some of your analyses based on your previous results, then this is also another way where you end up with biased results, which don't tend to generalize very well. It's generally more obvious when people do in like their science experiments rather than their deep learning paper, but it's still an easy thing to do, especially when you notice if you made an obvious mistake or something. This is also a reason we use 2 data sets to do our study, because yeah, we did play a lot with the first one, so we wanted to check that it still worked with the second.
May I also ask you a question?
Yeah, sure.
What is the impact of the n trials parameter? So if you chose, I don't know, to run it 10 times for each, how is it called, for each learning rate, do you expect a similar result, or how does that change in time? Is it relevant or just arbitrary again?
So let me go back to the random search. The n trials tells me how many parameters do I want to sample within this boundary.
Okay.
When I've not actually tried changing this parameter for the grid search, but what I think happens is if you do n trials equals 1, it looks at the first learning rate and then it stops. So okay. it doesn't search your whole grid.
Okay, so it's just the same number. Okay. Don't worry,
also,
I'm stupid. Okay.
Optuna has its own random state, which I haven't been able to change. So it shuffles the order in which it tries out these learning rates. That doesn't matter if you try them all. But obviously, if you only look at like the first one, then yeah.
Okay, I see. Thanks.
Okay, so my study has run. So now I can retrieve the best parameters from that study. So again, how Optuna works, and load it into the DNN. And then similarly, I can calculate the correlation coefficient with the actual envelope using that learning rate. Oh yeah, I changed this earlier, sorry. If you changed it like me in the task, you'll have to get rid of this -50. And I potentially end up with the same thing. 0.192. 0.198. So okay, these test scores are different numbers, and this one is higher. If it's significantly higher, I wouldn't bet on it. But if you do this process for different participants, you can see some quite big differences between the population hyperparameters and the subject-specific hyperparameters. Frank has sent us a message. Learning rate. Whoa. Frank, where is this from?
I ran this morning. It's on a data set. I was just playing with learning, different learning rates. And yeah, just if you check the numbers, I mean, the difference is quite small, but really change the accuracy of the neural networks. Yeah.
Cool. Can I ask what is the accuracy figure?
This one was for classifying pictures, your image, just a binary classification. Yeah, but you can see the difference between the validation test, for example, or the train. Yeah.
That's a cool figure.
One goes to 70% and the other one reached 40%. And just by changing the learning rate, the same neural network, same architecture, same data set, is just by this tiny difference on the learning rate. Yeah.
Sure. Nice. Thanks for that. Okay, so for the exercises, yikes, I feel we're not going to do this one. That's okay. I have some backup data. How does retrogression compare against the FCNN? So in this cell, my suggestion was to split up the test data into 10-second windows so that we have multiple correlation coefficients, and then we can do some kind of statistical test. So a t-test between the correlation coefficients which were achieved by the DNN versus those which were achieved by the linear model. So when I split up the test data into 10-second windows, this is the histogram of reconstruction scores that I get. So I get a lot around 0.17 or something. So yeah, this exercise is basically we want to split the FCNN predictions into 10-second windows as well and do a statistical test. So I'm going to do that. I'm going to use this function. Sorry, I used 5-second windows here, not 10 seconds. This function divides the data into 5-second windows and computes the correlation in each window, and then it returns all of those correlation coefficients. So I'm going to put in the envelope, the FCNN predictions. which don't exist. I missed an S here. Okay. And then I can do a t-test between the scores which are in this histogram and the scores which are in this histogram. I guess I can use rel. So this is a paired t-test. Yeah, I'm just writing really bad Python now, sorry. Okay, and it and they didn't come out as statistically different. That's interesting because that's not what I got before. Maybe we can play with some different window sizes, see what happens.
You shouldn't. Okay. Reach scores and FCN scores.
No, I'm not going to do that. Interesting. Maybe for this participant, they were very similar. We can, of course, test that. I should have printed them both out. Okay. So that explains that result. So for this participant, the ridge reconstruction was very similar to the FCNN reconstruction. At least that's what appears to be going on. Wait, yeah. Yeah, so that's why we didn't see a significant difference. In fact, we did see that for a few participants on the subject level when we did this in the paper. So, I mean, I guess this result can make sense. I'll admit I was expecting there to be a significant difference, but clearly when I fitted them, there wasn't. That's okay. Okay, I suggest, as it's 5 to 8, we move on to the analysis notebook, which is a lot quicker. There's no waiting for things to train. It's just compare. It's 5 to 8 in the UK, sorry. Just compare the linear models against the nonlinear models. So again, you can go to Colab, Microboot, ML decoders, and you can select part 3. So, okay, I had hoped, turns out we didn't have enough people to do this exercise. I had hoped we could each train a DNN and then analyze our results together. But I have some backup predictions already uploaded. So I suggest you comment out everything in this cell except for the bottom line. And even if you're on a machine which doesn't seem that fast with the DNNs, this notebook should run relatively quickly. No need for GPUs. Yeah, so you can start by installing the necessary stuff. This is just telling, this is a variable saying where the results are stored. So that's in data. In this folder, we have predictions from all 13 participants for each of the 3 models. So Ridge, the FCNN, and the CNN. And we can compare these against one another. So these lines of code, these are how you load those predictions of the speech envelope for each of these models. So this is how you load the predictions for the linear model. So in this case, we're looking at participant 0. We are accessing this file. Helps if you run all the cells in order. There we go. Similarly, we can load the FCNN predictions for the first participant. So we're loading the contents of this file now. We're also loading what the actual speech envelope values were here. Yeah, interesting. So this score is a little bit lower than what was in the other notebook. I mean, it could just be chance, like we used 3 parts before, whereas this model was trained on 9 parts. I'm not really sure why that's happened. But yeah, we can compare the time series, so the predictions, say from the CNN, against what the actual speech envelope was here. And yeah. So Giovanni says he's getting an error. Yes, I would recommend commenting out these top lines and just using the last line. In a second, so. Yeah, so yeah, this is what the CNN predictions look like compared to this 20-second window. Thanks, Judith. Versus the actual speech envelope. You can see they're not that similar. Apparently, this is what a correlation of about 0.2 looks like. But of course, when we did the significance testing earlier, we saw it was still significant compared to chance level.
I have a question. So the reconstruction goes negative too, but the envelope is for sure a positive signal. So I was wondering if there is a way to constrain the outputs of the neural network to be strictly positive, so you avoid a lot of, yeah, you can improve the correlation. And
you can't control what the correlation is going to be. So the yeah, if I predict the speech envelope using my neural network, and then I correlate it against the actual speech envelope, I can't control what that number is at that stage. Like I can't control what the correlation coefficient is going to be.
No. I'm just wondering if you can constrain the neural network to output a positive reconstruction. So the envelope I see in the plots, it goes negative, but the energy can't be negative, and that's a prior knowledge you have all the time. So I was wondering if this can help somehow. If this is easy this is an easy constraint to put in the network.
Yeah, it is an easy constraint. And I think it's a good idea. It's not something I considered. Yeah, I think it'd be worth looking at. I did try in post-processing, trying to stop the reconstruction from being negative or below what the zero level is. And that didn't help. But I think it's a good idea. It'd be worth
in post-processing, you're not helping the learning.
Yeah, so I agree that
if you put the constraint in the network, it's possible that you help the network to learn better because you narrow a bit the space of solutions, maybe.
Yeah, I think it's a good idea. Like, it makes sense when you know the outputs can't do something. It makes sense to impose that as a constraint. So yeah, I think it's a good idea.
I agree on that. I mean, the point, Georgia, there is, if you know, is it just the constraint of being negative? Maybe it's not just that. Maybe the constraint should be, it should look like an envelope. You know what I mean? With a number of elements, a number of constraints. The fact that it's non-negative, the network could just, since it's already optimized to find whatever is the bias function now, the solution would be, oh, just shift everything more positive. That will satisfy the constraint. And that's the risk. But I agree. We tried also with the TRF to do that, right? And the thing is that if the goal function is the correlation, it doesn't improve the correlation to do that, but it leads to a better result. So the question is, what is that you're trying to optimize here? Is it just your error, your correlation? Or is it also, that what you get is a viable envelope? It's a useless waffle, what I said, but it's not as simple as saying, don't make it negative.
Yeah, it's not just about the correlation. It's also about interpreting, right, the TRF, right? So your transfer function should be able to recognize that the EEG response to silence.
Yeah, at the same time,
somehow,
the EEG always goes ups and down.
That's
the problem,
exactly.
Right? So the EEG never stops. So if you have if your model is just a multiplication of your stimulus, how do you make it zero? It's challenging.
Yeah,
it's a great point, Georgia. It's something I've been thinking about, and some people have been thinking about, let's do an extra step afterwards. Whatever reconstruction you get transform it into something more envelope-like. But in terms of interpretation of the EEG or of the TRF, remember, this is a backward model, so we don't really interpret the TRF here.
Right.
But I agree. The problem is that the EEG goes ups and downs. So yeah, it's a challenge.
Yeah. I don't know. I think
anyway, behind interpretation, I think it might help the optimization thing. If you put physical constraints, that are valid all the times, like energy is positive.
Mm-hmm.
So this, it's valid always, and it might help.
Yeah, I think I agree. Just like, yeah, there's no reason why it should be predicting negative things, even if it does go up and down. Like, I accept that it might not change the correlation coefficient, but it may just be like wrong in a different way in the places where it's negative. But I agree, it may help with the optimization. It's also quite it's probably quite a simple thing to implement. It's like add a sigmoid or something at the end and see what happens.
Yeah, I was wondering what. Yeah. Okay.
You can also consider, one thing I'm doing with the student now is you're reconstructing multiple things, right? So you reconstruct the envelope, and then you do the reconstruction of an onset detector, for example, and then you can combine the two in a next step. I still agree with Giorgio that it could be cool to have a constraint within the model, but that's one trick I'm trying.
Wait, you're combining a reconstruction of an envelope with a reconstruction of an onset envelope, or you're doing onset detection?
It's more complicated. It's a spectrum with other stuff, pitch and everything, and to make it look more like speech, we are trying to get a model that is specifically detecting where the sound is, and then you just zero out whatever in the envelope. That can help, especially with rhythmic stimuli. If you have music, that makes sense, because it's just much easier to do. With speech, it's not easy to do.
Yeah, these 0 points I think are actually a challenge for especially the attention decoding stuff, where if someone's just stopped speaking for a moment, like, does your decoder switch to someone you don't want to listen to? Yeah, it's a thing that hasn't really been addressed, I guess. Okay, so in the talk, someone asked how similar the CNN and the FCNN were. And the answer turns out to be quite similar. So that's what this exercise was basically about. Okay, correlation was not as high as I thought it was, but it's still pretty high. Like, this is much higher than the reconstruction of the actual speech envelope. The two DNNs have a correlation coefficient of about 0.6, 0.7. It's pretty high. Yeah. We can look at how it looks for all 13 participants. So I'm just loading the predictions for each participant, and then correlating them together. Yeah, so you see the CNN and the FCNN spitting out quite similar predictions for each of the participants. Interesting. I did think it was higher than that, but they're still pretty similar. I guess one difference is there was a compressive nonlinearity at the end of the FCNN, I think, which makes things slightly different when you plot the predictions against one another. And yeah, if I were to repeat this, say for the linear model, I think you find that the DNNs perform more similarly to each other than they do to the linear model. Yeah, so you get some lower correlation coefficients. Okay, so the final aspect of this is the population level analysis. So do the DNNs actually outperform the linear models? So the idea here is that we calculate, in this case, it's just the trial-wise correlation. We calculate the trial-wise correlation between the predictions of each model with the ground truth. And then we compare them against each other. So I'm going to show a plot of what I just said, so that makes sense. Yeah, so in this cell, we collected the reconstruction scores and the null reconstruction scores for all 13 participants and for each of the 3 models. And then we've plotted those 13 scores in each of these box plots. The null scores are on the right. And here's the thing I was talking about, they all turn out to be negative. And in fact, when you correlate the speech envelope against its reverse, you find that that comes out to be negative. And as we were discussing, that's why I think this happens. Yeah, so you get this value of minus 0.05, which lies around here. So I think that explains why these so-called null scores have this systematic offset, where they're all a bit negative. There are different ways you can account for this. So you could maybe try doing permuting the speech envelopes. So maybe placing an offset between the envelope and its prediction, and trying lots of these different offsets to build up a distribution, which should have zero mean. And then you can use this as your null distribution instead. Or you could do what we did, which was divide it into 2-second windows, or however many you like, and then find the correlations between unrelated windows. And there should also not be a systematic offset there. You should get a median of 0 in these distributions. So yeah, that was my answer to this exercise. And finally, we can perform some t-tests between these 3 box plots. So you can see if there's a significant difference between the CNN and the FCNN, or if there's one between the ridge regression and the CNN. And in fact, we find that there is between the DNNs and the linear regression, but there's not a significant difference between the DNNs, which is probably to be expected from the diagram. Okay, so I think what's maybe more interesting about this stuff is maybe the attention decoding, which I said was an extension because I thought the rest of these notebooks might take a while. But the data is there if you want to play with it. So, I mean, I'll just step through these cells to show you. You can find the reconstruction score for the attended speaker and the unattended speaker. This is using DNNs that were trained on the 2-speaker, that were evaluated on the 2-speaker data. So there are various things that you could consider. So maybe you could look at not using the correlation coefficient, but using something else as a metric for an attention marker. You could look at, similar to Giovanni's question earlier, do the DNNs reconstruct the unattended speaker better than the ridge regression? You could look at different window sizes for decoding accuracies, and that kind of thing. But yeah, that's just if you want to do it. I think we went through some useful points about some of the technicalities of DNNs. So like the hyperparameter discussion, I think was good. The discussion of whether these null distributions are really useful. Yeah, that brings us to the end though. So thanks a lot for staying all the way. You did. Yeah.
Thank you very much, Michael. Does anyone have any question? No, I think.
Can I ask a quick question? Sorry.
Yes, sure.
Can you? I was just wondering if what's the minimum amount of data that you have to train these models, in that, you know, you are quite rich that you have 15 trials, like 40 minutes of data, but when you're working with pediatric data, we can't have this luxury. So I was just wondering what's the minimum you will go with?
So for our second data set, we had 2 speaker data, and we really wanted to look at decoding attention. We only had 10 minutes. So what we tried to do is we had several listening conditions. We tried to train the DNNs on 10 minutes of clean speech data and then apply them to the 2-speaker data. And that didn't work at all. And basically we had to keep on adding more data until it worked. So we added some speech and noise data, some other data, and we ended up with needing about 20 minutes of data to make it actually work. And this actually happens to be how much data we used in the first place on the first data set. We used 9 trials at like 2.5 minutes per trial. So yeah, my feeling is that you need about 20 minutes of data to make it work. And I think you can actually see a few papers doing exactly this, where there are some mixed results, where sometimes it doesn't work and sometimes it does, but it works. Maybe less well, or it's more noisy than it was in the Detaille original paper. And that's potentially just because of data constraints. So yeah, my feeling is that you need about 20 minutes, at least when you're using data that was prepared in the same way that ours was.
Okay, but this would be 20 minutes of continuous speech basically, and like a single condition, and like assuming that also EEG quality is good across the 20 minutes.
Yeah, so one thing about what I said was that we did mix together a few conditions. I mean, it was always reconstructing the attended speaker. So maybe that makes the optimization a bit harder. But yeah, you do, like 10 minutes for sure was not enough to get something to work. 10 minutes of clean speech.
Yeah, I think I'm doing. It's just like
Thank you.
Thank you.
Thank you very much. Someone else has questions? Okay, I think we are done. Thank you very much, Michael. Thank you for your talk, for the tutorial. It was very nice and clear. And I just want to remind that tomorrow there will be another session with a talk from Giacomo Baruzzo and a discussion. So hope to see you there.